Next. Okay, cool. All right, we're good.
All right, it's my pleasure to introduce Liz Munch, and the title of her talk is Bounding the Interleaving Distance for Geometric Graphs with the Loss Function.
Excellent. Thank you so much, and sorry for the technical difficulties. I'm not going to blame Harvard, but I was kind of hoping it was going to define interleavings for me first, but that's okay. We've got some interleavings defined on here. So what I want to talk about is thinking about interleaving distance in a bit of a different setting than we were doing for the last talk. So I'm going to be interested in more graph-like objects. And so the use case I'm going to have in mind, although it's not necessarily what we need to restrict ourselves to, is the following. So we've been thinking about things related to geometric graphs. And by geometric graphs, what I mean is you've got some sort of combinatorial graph, which I'm going to treat as like a topological space, at least in some settings. And I'm going to have some sort of map of my graph into the plane. And for the purposes of a lot of the things I kind of want to do, I'm going to assume things like planar embedding. For a lot of the stuff that I'm talking about, this isn't quite as necessary unless you really want to get specific about algorithms. But this is kind of the use case I have in mind of what we're going to be doing with this. And so what we're going to do is we're going to start thinking about comparing geometric graphs. So I've got two of these things embedded in the plane, and I want to talk about the distance between them. So I want some number that gives me some comparison between the green Y and the purple X object. And the way that we're going to do that is by thinking about things related to interleaving distances. Now, clearly there's been a lot of work on this just as a general subject area for a while. My apologies if you think your name should be on here and it's not, and you should yell at me later, and I'm happy to add it on because I'm sure I missed somebody. But the idea here is that the interleaving distance, or the concept of interleaving distance, started when we were thinking about generalizing bottleneck distance and things like that to single parameter persistence modules, but then has just expanded into all these different frameworks where you can actually use these ideas to come up with distances. And a lot of it comes down to thinking about these things in sort of a categorical framework where you can start comparing these objects in a similar way, even though I wouldn't have intuitively thought that any of these things would be related. So for the stuff we're going to talk about today, we're largely going to focus on, mouse, oh, no, this mouse is there. That's my mouse. So we're largely going to think about more of the graph type things, right? So if you like to think about this stuff in sort of a categorical framework, you've got stuff that's represented by functors, and your functors are probably going into something that looks like set. All right, so I've done a bunch of stuff thinking about this related to Reeb graphs. Sort of the most closely related one would be things like formograms. But for what I'm going to talk about today, I'm going to think about things that are closer to sort of a mapper graph style approximation, some sort of discretized version of all of my information where I can come up with interleaving distances. All right, so the problem is, as we saw in the last talk, in many settings where this is interesting, interleaving distances are difficult to compute. Right? And so we still want to compute any of this stuff. And so we found this paper by Michael Robinson, where he was doing something in a completely different context, but sort of the inspiration for this work. So he was interested in understanding things about data fusion. And in doing this, he was trying to come up with measuring how far a particular functor was from having a section, right? So he ended up looking at all of these natural transformations and maps and things where you kind of almost had the commutative diagrams you wanted for whatever categorical setting you were in, but not quite, right? And so he called these things assignments. Now we're going to use the same name because I like it, but it's kind of similar in spirit, but a bit different in definition. On a side note, for all of you category theory minded people, I'm trying to find any example where people are using non-commutative diagrams in literature. So if you find one, please tell me. Right now, the example I have is NCAT There's one person who about 5 years ago posted the definition of an unnatural transformation. And that's pretty much what I got. So if you know of anything else, I'm very interested. But the whole idea here is that we're going to mess around with things that kind of look like the natural transformations we want, but don't quite satisfy all the properties we need quite yet. Okay, so here's how we're going to get away with figuring out how to compute interleaving distance looking things. Okay, so for my use case at least, I'm going to make everything nice and discrete and finite so I can deal with it. So what I'm going to do is I'm going to take the place that I've mapped all of my graph data into, R2, and I'm going to discretize that thing. I'm going to take my given data, I'm going to encode it as a cosheaf, right? So this is going to be taking connected components over open sets that have something to do with being restricted to this grid. And I can create an interleaving distance that way. So I'll tell you what that is in a little bit. And then the game is going to be, if you give me something that's not quite an interleaving, we're going to build a loss function where not only can I use it to build a proper interleaving, but I can tell you a value for which you definitely have an interleaving and therefore give you a bound at least on your interleaving distance. So that's going to be our goal today. So the main thing is going to be coming up with whatever the heck this loss function thing is. Okay. So first, let's get a definition of this distance itself. All right, so I want to discretize my base space, and the nicest way to do that at the moment is just to mess around with cubical complexes. So the cubical complex, all this is you take vertices on a very nice grid. I've got edges that go between the vertices, and I've got the squares in the middle of the vertices. And I can do this in higher dimensions, but again, I'm just going to draw my pictures in R2. Right? And I've got things like face relations. So I've got an edge is a face of the square that it's attached to, the vertex is a face of the square, etc. Right? And then, so this is going to be our cubical complex, which I'm going to call K. And for the purposes of making everything behave itself, I'm going to guess everybody's going to be living in some bounding box, so everything's going to be finite. All right, so what do? I'm going to take this grid and I'm going to give this combinatorial pile of cells a topology. And I'm going to do that with the Alexandrov topology. So the idea here is that an open set is now, so we're going to use upsets as our open sets. So if you give me any simplex, so for instance, my vertex, the upset is the collection of everything that is an upper face of me. Which I think, no, coface? Yeah, coface, right. So it turns out that the coffee shop we went to this morning, a large latte has 4 shots of espresso in it, and I found that out after, so we're fine. Okay, so a vertex has an open set associated to it, and it's basically the collection of squares and edges around it. The edge in the middle has the squares, and the top level cells, my squares, they are their own open set, so that's it. All right, this thing gives me a basis for this topology on this grid discretized setting. Right. And so what I can do is I can take my information from my geometric graphs and I can encode it as a cosheaf in the following way. So I have my open sets of K. So that's this discretized thing I was thinking about before. And for any open set, I can check the connected components in the inverse image of F over the geometric realization of that open set, right? So for instance, if my open set is this orange U over here, it's how many connected components are sitting inside of this box. And in this case, I see 2 of them. One of them is the one that's got the point A in it, and the other one's the one that's got the point B in it. And so those connected components are represented by the capital A and B over here. And we have all sorts of nice cosheaf properties, because if you include U into V, then you have maps from your connected components over U to your connected components over V, right? And so in this case, A, there's a connected component in the blue region that it's part of. B is one in the bigger region, and then we just see a new connected component when we expand ourselves out that far. All right, so this is going to be how I'm going to take all of my geometric graph data and encode it as some sort of cosheaf construction. All right, now, if you're going to do an interleaving distance, you need some sort of thickening or smoothing operation. And so in this case, what we're going to do is essentially a discretized thickening just in this fixed grid place, right? So I'm going to define the end thickening of an open set as follows. So I can take the up set of a set and I can take the down set of a set, right? That just means take everything who's upper adjacent or take everything who's lower adjacent from you. And so in our case, the one thickening is going to be take the upset of the down set. Yeah, so go down first and then go up. So in our case, if I started with the open set, which was this purple, the down set of that is the basically including all the stuff on the boundary, and the upset of that is the squares on the outside. So the one thickening of this particular open set is all of the green stuff, well, and the purple stuff. Okay, so now I have this thickening operation. And what I can do is I can define an interleaving distance, right? So the game with the interleaving distance is, I've told you what this thickening operation is, and I've got 2 of these things I want to compare. And so what I'm going to do is I'm going to try to find natural transformations that go from one to the n thickening of the other, the second to the n thickening of the first, where these triangle diagrams always have to commute, okay? And then the interleaving distances, find me the smallest number for which I can actually find that thing. And again, I've discretized everything, so now my interleavings are integer valued beasts. And of course, this thing we can prove very easily as an extended pseudometric because it fits into the Bubenek-Scott framework, and so poof, I have a distance. Okay, so what's happening under the hood? There's two things I'm trying to do. If I'm going to find an interleaving for you, first off, I have to make sure that they're actually natural transformations. And second, I have to make sure that that thing commutes for anything I can possibly find, right? All right, so here's where our idea for a loss function comes in. All right. I'm going to define an n assignment as something that looks like it should be a natural transformation, but I'm not going to make you any promises about commutativity, all right? So if this phi, so phi is a natural transformation means it's a map from f of u to g. Oh, sorry, I'm swapping out notation, but this is the thickening operation on a particular location. What is this thing? Phi u and phi v should make all of these diagrams commute for anything that I can find. And if they do commute, then this thing is a natural transformation, but I'm not going to promise you that for several slides. Okay, so when I say n assignment, it's a natural transformation with no promises. Okay, so if I hand you two of these n assignments, the phi and the psi, I have to run around checking whether or not all of these diagrams commute, right? So in order for me to promise you that the things I handed you are an interleaving, I need to check that all this stuff commutes, right? And so essentially the things on the left are me checking that phi and psi are actually natural transformations. And the things on the right are me making sure that they satisfy the interleaving properties. And for the sake of trying to write things down later, because we put these diagrams all over the place, we started swapping out notation. So the parallelogram notation should match up with the parallelograms and the triangle notation should map up with the triangles. And so when I write that down, I just mean that diagram that I don't want to write again. Okay, so the other ingredient that we need, and this was the really nice idea that came out of Michael Robinson's paper, is I'm going to define a distance on the sets for every f of u or g of u for the other one. All right, how am I going to do this? Okay, so fix one of your f of u's. So I've got an open set. So for the moment, which one did I do my example on? Oh, I did on both. Okay, I've got f of u. And so what I'm going to do is I'm going to define a distance by looking at the following thing. I've got two objects in my f of u. They represent connected components. How far out do I need to thicken my particular open set before those two things are in the same connected component? Okay, that is what that thing says in notation, right? So if I take the thing representing A and the thing representing B, and I push it forward by K, how far do I have to go forward by K before they are the same image under these maps? And so in particular, for the example with A and B in f of u, if I thicken out by one box, they are the same connected component, I hope. Yep. And for the other one in V, if I expand W and Z, going out by one, they're not in the same connected component yet, but going out by two, they are. Okay. And then if there is no n, then I'm going to set infinity and then try to get rid of those cases later. Okay. So there's my distance. And so now I have a loss function. So I handed you natural or n assignments that don't necessarily commute, right? And so if they don't commute, what that means is I can start with some object up in f of u, and I can follow around the parallelogram, and I get two different things over here. And so then what I can do is I can define my loss function by saying, how big does k have to be before those two things are the same, right? So if I have some alpha, and I start in the top left, if I follow the purple side around and down and go forward into k, that's the purple highlighted thing up there. If I follow down and over, that's the blue thing over here, right? And so the idea is, what's the over all of the alpha in your f of u, what's the largest k needed so that everything will commute by the time I get there? Okay. Yeah, so translation, the idea here is my loss function is rigged where if my loss function is 0, then my parallelogram commutes. Okay. So here's my example. So this is me just drawing all the diagrams that you want for a particular example up in the same top corner, right? And so in particular, what I can do is I can mess around with, do I have the, oh, yeah, I do, okay. So I can calculate the distances for all of these pieces, right? So I'm going to be interested just in that U that's in the center, and I've got U1, U2, and U3 marked. I've got the distances I can calculate for all the pieces. So for example, the distance between Z and W is 3 in the original. But when you do the thickening, it actually decreases. Right. And so then the idea is that if I handed you an N assignment, so some choice of maps, right? I can go measure what the loss function is associated to this assignment. So let's see if I can find the example. Is this going to show? Yeah, okay. All right, so let's see. So if I'm interested in the map where I'm going to take phi sub U, so he's the one that goes, oh wait, do I have my highlighting backwards? Oh, no, there's psi sub U. This is the one over here. Sorry, let's do psi sub U. So psi over here sends W and Z to A prime. It sends W prime and Z prime to A double prime and B double prime, respectively. And so if you go check who's commuting where, all right, so W and Z are two objects over here. They both go to A prime in the top, but they go to different things if they go down and around the bottom. Right. And so what that means is that my loss function is actually 1 because the distance between A prime, A double prime, and B double prime in this particular location is 1. Right. Okay. All right. So I've got a loss function for parallelograms. I can come up with a loss function for triangles. Right. So in this particular case, it's the same idea. I take an object over here in f of u. I follow it around my triangle, and if they don't go to the same place, how far forward do I have to go before they do land in the same place? Okay. Similar trick, if my loss function for my triangle is 0, then my triangles commute, and I'm happy. And so we can do a similar thing with the same example, right? So in this case, if I follow along this triangle, W and Z, again, still go to the same place up top and then come back down to W double prime. If I follow along the bottom, they go to the two different options, and the distance between those two things is 1. Okay, so there's a little bit of an annoying thing. What I forgot to point out was the fact that there's a ceiling function with a 1/2 here. This has to do with weirdness with interleavings and the fact that this thing actually goes to 2n. But the rig is still the following. I'm going to have a k for which I get out to this 2n plus k thing, and what I want to have commutes. All right, so if I go back to my loss function and I'm careful about it, it's the ceiling of 1/2 times the distance I had. And so in this case, it ends up being 1. All right. So now I have loss functions. Not a lot of time. All right. Okay. So the loss function is just take all these diagrams in sight and find the worst one, and you take the max. Right. So what's going on here? Every possible pair of open sets U and V, not necessarily just basis elements. You just handed me every possible open set information, and I'm taking a max over those as my loss. And so it turns out that if you chase all this information around, if you give me 2 N assignments, so you are just like some random person has handed me N assignments, I have no control, I could have done very dumb things with them. The theorem is that the interleaving distance is N, so you chose an N when you handed me your possible interleavings, plus this loss function, right? Because basically the loss function is rigged so if I go forward far enough, everything that I wanted to have commutes. And the proof, once you get the right definition, is actually relatively simple, because what we end up doing is just creating an interleaving by pushing forward the not quite an interleaving you had before into one that is actually an interleaving, and then spending a bunch of time checking that all the diagrams you could possibly want commute. There's some annoying technicalities, which are basically all the little specific things you need to check to make sure that, given the fact that your loss function is k, that this extended beast actually commutes where you want it to. All right, that looks icky, but it just says everything commutes. Okay, let me get to the second bit. Right, so computational issues. So we've been thinking a lot about exactly how to compute this distance. And this has to do with complexity of the embedding and sort of your input information. So that's something we're working on. But the other problem that I can immediately talk about is the following. Combinatorially, if you hand me all of this data and I say, you need to check this thing for every possible open set on this grid, that's not fun, right? Because open sets here are not only just like individual, connected components, they can be unions of connected components, they can be strangely structured. There's way too many for me to ever want to deal with. So it turns out that we can do something more intelligent than what I just did. Okay, so what I can do is I can just focus on the basis elements. All right, so all I'm going to do is I'm going to swap out everything I just said and only care about the open sets that are specifically related to cells from the original K. All right, so my basis n assignment is a collection of maps where my open sets have to be the ones that are the upset of some particular cell in K. And it's just the information that comes from those pieces, right? So now I'm doing my collection of open sets over all the cells in K rather than over all the open sets. I only have to store the maps from the basis elements, and I can, or alternatively, I could have taken, you handed me some full n assignment, and I just forgot about all the information you told me about the things that weren't basis elements. All right, so the basis loss function is what happens when I only deal with the diagrams that come from the basis elements. Right, so here's what's cool. I can do the same thing I did before, but only with this basis version, right? So the only thing I've changed in here is that I've only told you stuff about basis elements. My loss function only has to do with basis elements. And what's took me a while to be okay with was the fact that this is somehow computationally better and has a lower loss function or a loss value, right? So for instance, the loss function we had from before used all possible open sets, and now we're using a subset of those and taking a max over a subset. So this is actually a smaller value than I had from before. Right? Okay, so the proof sketch is very similar. We end up just extending to this. You spend a bunch of time trying to check all the basis stuff works out. But for the sake of time, let me try to say a few things really quickly. I know I'm over already. So the first thing is computational aspects, right? So part of the reason that we're doing this is because I really want to be able to compute interleaving distances, but as everybody has seen, this is probably not something I'm going to overcome. So instead, if I can come up with some method for, say, gradient descent or improvements, you hand me not an n assignment, and I can tell you a loss function, which means I can already give you an interleaving, but then also can I try to make it better using, I don't know, some sort of local update method? Can I improve this thing until I get at least a local optimum for my interleaving distance? And I still get an interleaving from whatever you hand me. Not necessarily a good one, absolutely no promises anything is tight, but at least I can give you one. The other fun thing with this is, I think there's a lot of really interesting generalizations. The framework and all of the loss function stuff that we did was entirely categorical. And so it doesn't really matter if I hand you geometric graphs, it's just kind of easier for me to try to draw the pictures. In particular, if you drop a dimension, you end up with mapper graphs. And so I think a lot of this we can use for computing or bounding the interleaving distance between mapper graphs. I'd be really interested for the more algebraic minded folks, if you want to think about whether or not this is the kind of thing that would work for like multi-parameter persistence, because we've got all these vector spaces, but now I have to do distance in vector space land, and that's where I'm a little fuzzy. But in general, I think this is kind of an interesting way of trying to bound this problem. So yeah, so with that, I will point out, so the paper is available, although we're working on updating it, so it should have the algorithm stuff soon. Thank you to my co-authors, so Aaron, Bay, and Sarah, and thank you to all of you for listening.
So you answered almost. I was wondering why you restrict everything to geometric graphs.
Pictures, 100%. That's it.
Only pictures. So
Yeah, no. So we're working on doing the mapper version because that one's basically immediate. The geometric graph version is partially because the algorithmic choices come down to trying to figure out when two things are in the same connected component and the thickening that you need for that. And that seems to be a nicer framework to work with in terms of the computation. But there's no reason why the input had to be graphs, right? You could have sheets of things, you could have much more complicated topological spaces. I want to say you really want to have the things you're comparing to both have one connected component, or you have infinite loss function problems. And you really want to have your sets of things be finite, like, so the set of connected component over any of those cells should be finite. And in that setting, everything I said with the categorical loss function should follow through just fine.
So it seems like your loss function, your loss function is really dependent on everyone grid you have.
Hmm.
So is there anything you can say about it if you maybe refine the grid or
That is absolutely a very interesting place to go next. So first off, I can define this loss function on any sort of poset base structure. And it would just be sort of a finite increasing. Now, it's not going to look quite as nice as the like outward spreading things, but yeah, there's nothing stopping any of this from defining this on any sort of poset structure you want. And then, sorry, I already forgot. What was your second question?
just about like the refining or
Oh, yeah. No, we haven't messed around with that, but that would be very interesting to do, right? Because if you had a refinement of this, I don't know, I think that's a very interesting direction to go, and we haven't fought with that yet. Mhm.
There's a question in the chat.
Hmm?
Is it a good idea to construct a Cauchy for a planar graph? It seems that the geometric simplicial complex can also be done in this way.
Yeah, so I think that's related to some of the other questions. Yeah, so everything that I'm saying, you could have much more complicated embedded structures. And also, I mean, you can do higher dimensions. So if you have any sort of structure with a map into RD, you can grid up RD into pieces and everything I said falls out, right? So, yeah.
So when you pass from all open set to just the basic open sets, you both improve like computability and you get a better bound. Do you lose anything at all?
No,
Or is
and
like
it took me a long time to convince myself of this. Okay, so here's, let me tell you, there were like multiple research meetings where we're like, why is it going down? No, okay, so here's what's basically going on. Somebody out in the ether handed me an assignment, and they handed it to me for every possible open set, but they didn't check anything related to compatibility, right? So they had it for all the bases too, but they didn't make sure that, like, if I have these two basis elements and I do the union of them, they didn't make sure that that made any sense whatsoever. So essentially those choices could have contributed to your loss function, and I'm just going to ignore them. What I'm going to do is I'm going to take just the basis element pieces, extend intelligently to the higher, the unions and all the other open sets, and then use that as my loss function. And so I'm still like, whatever problems you handed me on the basis functions are still there, but I've somehow gotten rid of at least some of the dumb choices you might have made on the rest of them.
Last question, over.
yeah, I was wondering if this basis, if they can actually be different, these two loss functions, the general one and the
Great question. We have not sat down long enough to find an example of that, but that's if it feels like oh no, wait, I think we had an example at one point, and again, it kind of went back to the same idea where we just made really dumb choices with the union of things and made sure that that was causing your actual loss. Oh, was it one of my examples? Oh, well, that was smart of me. Look at that. Did I do? Was it the original?
Close over here. No.
Is this somehow connected to the fact that when you define this, interleaving, you're starting at one cell, you're not starting at, let's say, two different cells?
Yeah, exactly, right. And yeah, and so if you want to make the first loss function bigger, yeah, you've got some sort of choices on the smaller basis opens, and you make just a really dumb choice on the union one, right? Because again, I'm handed an assignment that I didn't have any control over, right? And so it can be as awful as you want, because if I'm not requiring commutativity, right? What's really fun is you talk about non-commuting diagrams in front of category theorists, and they all just get really nervous.
All right, let's thank Liz one more time.